Hi, today I'm going to walk you through my machine learning pipeline for wildfire burn area detection from satellite imagery. It tackles one of the most critical environmental challenges of our time, rapid wildfire damage assessment. Traditional field survey to map burned areas takes weeks, costs thousands, and puts surveyors at risk in dangerous terrains. This is where the European Space Agency's Sentinel-2 satellite constellation becomes crucial. Sentinel-2 consists of two identical satellites that together capture the entire Earth every 5 days at 10-meter resolution. A key is that it doesn't just see visible light like our eyes, it captures infrared radiation, which reveals vegetation health through biological process. We measure vegetation health using the Normalized Difference Vegetation Index. It's calculated as near infrared minus red divided by their sum and gives a number between -1 and 1. Healthy vegetation is around 0.7, stressed areas are around 0.3, and burned is often below 0.2. But for wildfire specifically, a more accurate index is a normalized burn ratio, which uses shortwave infrared instead of red light, and NBI is better at picking up things like char and ash after fire. In this study, I evaluate three machine learning paradigms. Supervised learning involves training model on labeled database where each input is associated with a known output. The algorithm learns to classify pixels as either burned or unburned based on these labeled examples. Unsupervised learning, by contrast, doesn't rely on labeled data. Instead, it identifies inherent patterns and structures within the database. The random forest algorithm constructs an ensemble of decision trees. Each tree independently makes a classification, and the final output is determined through majority voting. Convolutional neural networks are a type of deep learning model particularly well suited to image data. They apply a hierarchy of filters to extract spatial features, starting from low-level edges and progressing to high-level representation of burn patterns. K-means clustering is an unsupervised algorithm that partitions data into clusters based on spectral similarity. Pixels with similar reflectance values are grouped together, and post-analysis interpretation determines which clusters correspond to burned areas. And now onto our cell implementation. We have the introduction of what is going on, and we also have the essential libraries that all cells, if the library is being implemented in that cell, has the import beforehand. Firstly, we have to mount Google Drive, as the organized directory structure saves all files systematically and gives free access to storage. Also, we are connected to the pins JSON file, which contains pre-validated wildfire coordinates and temporal metadata for systematic data acquisition across all three fire regions. And going forward, we have the environmental cost tracker monitor. It monitors our computational carbon footprint in real time. Every CPU operation gets converted into energy consumption and CO2 emission. It's crucial because AI research has hidden environmental costs that we need to acknowledge and minimize. Moving on, Cell 2 handles authentication with Copernicus database. When you run this, it prompts you to your Copernicus login where you write your username, which is your email, and your password. You can create a free account on their website, and it has an automatic token refresh, which is essential because downloading satellite can take a few hours. Losing authentication mid-download means losing hours of progress. Also, there is a comprehensive data handling which addresses real-world API challenges such as failures, rate limits, server maintenance. It handles the issues gracefully with exponential backoff and retry strategies instead of crashing. Cells 3 and 4 implement satellite data acquisition where every parameter affects data and quality and scientific validity. Fetch function converts zoom levels to geographic degrees, and we need 10-meter ground resolution across all fire regions for fair comparison. Cell 4 is the cell that fetches the data completely. We are using level 2A data because raw satellite data is contaminated by atmospheric effects, water vapor aerosols. Level 2A has these removed through atmospheric correction algorithms, giving true ground reflectance values comparable across all dates and locations. And we selected a few days window where it balances cloud avoidance while capturing immediate fire effects before seasonal vegetation changes. Cell 5 creates systematic quality assessment visualization, which is very important for selecting data, as detecting data problems would ruin machine learning training. A 3x4 grid shows each wildfire region with 4 standardized views: pre-fire RBG, post-fire RBG, pre-fire, post-fire NDVIs. This systematic comparison immediately reveals data quality issues, misalignments, or temporal mismatch. This serves as our validation step. Cell 6 begins the ground truth development, the most challenging aspect. We normalize the NDVI from 0 to 155 integer format to the scientific standard of -1 to +1 range. It's essential because satellite sensors capture data as a digital number for computational efficiencies, but scientific analysis requires physical, meaningful values. We have chosen different color scheme which leverages the human eye perception where red intuitively signals unhealthy and green signals healthy. Burnt areas can immediately pop out as red, making a visual validation intuitive. In this code, we get the pre-fire NDVI, the post-fire NDVI, the difference of the two so that we see what vegetation loss we may have had. Cell 7 shows systematic threshold selection through comparative analysis. From cell 6, I test 3 distinct approaches on identifying different areas with minimal remaining vegetation and looking at what threshold can signify vegetation loss. So after I apply the threshold in cell 7, we get the RBG burn index becoming our ground truth for training all machine learning models. The visual validation approach is scientifically valid as well. We also did a statistical validation for the visual threshold, providing quantitative rigor. So I analyzed statistical distribution of each index in burned versus unburned areas, and we get the results. We have a scientifically valid threshold. Cell 9 establishes our spatial validation framework, which is important for preventing optimistic bias that undermines most remote sensing machine learning studies. It's important because nearby pixels are highly similar due to shared environmental conditions. So when you have a trained test split, it would be placed in adjacent pixels in different sets, creating data leakage and unrealistically optimistic results. Published studies without spatial validation often show 95% plus accuracy and completely fail in real deployment. I would like to point out as well that Cell 9 defines all unified spatial processing functions that ensure random forest, CNN, and unsupervised methods use identical spatial validation strategy, which then in turn, Cell 10 executes the complete spatial feature extraction pipeline and creates the training data sets with the proper geographic separation based on the Cell 9. The training data has been split as such, where Greece has been just 80% training, 20% validation. Turkey is 70% training, 20 validation, 10 testing. And California has just been completely put aside. And then moving on, we have Cell 11 implements the random forest approach using spatially validated data set. I started an environmental tracking here to monitor the computational carbon footprint of each machine learning method. So at the start and at the end of the cell, we have a track which tracks how much carbon dioxide and such we've used. Random forest uses ensemble learning with 100 trees, balanced class weights to handle the natural imbalance between burned and unburned crystals, and stratified sampling to select representative examples from our large spatial data set. And we get a confusion matrix, F1 score, accuracy, precision, recall. Cell 12 creates a comprehensive spatial prediction map showing random forest results across all regions. The visualization includes pre-fire imagery, post-fire imagery, ground truth labels, model prediction, probability map, and error analysis. Cell 13, implementing the CNN architecture in training. That processes 32 by 32 pixel patches from our spatial blocks and includes a temporal approach that allows the network to both learn from spatial patterns and temporal changes simultaneously. Implementing a patch-based deep learning strategy. That Cell 14 shows the CNN training progress with learning curves for accuracy, loss, precision, and recall, convergence without overfitting and early stopping based on validation performance. And then moving on as well, we want to see a visualization. We've provided a comprehensive CNN evaluation, including both patch-based results and pixel-level reconstruction. And moving on to Cell 16, we begin the unsupervised environmental tracking, and the unsupervised machine learning training. Feature extraction uses identical functions as supervised methods, but critically, no labels are used during this entire phase. Cell 17 applies principal component analysis for dimensionality reduction. PCA finds orthogonal directions of maximum variance, typically capturing 85 to 95% of information. Cell 18 implements computationally optimized k-means with stratified sampling for 100,000 representative examples. Stratified sampling ensures representation across entire feature space while maintaining computational feasibility. Cell 19 provides a sophisticated algorithm. It gives a cluster interpretation using fire science domain knowledge. Cell 20 has a comprehensive evaluation with identical protocols across all three methods and ensures performance differences reflect actual algorithmic capabilities. And Cell 21 is the final environmental report, which produces an environmental impact assessment that tells you about the total project consumption with minutes, energy, and carbon.